my entry into this field of quantum information, was kind of from the kind of quantum optics direction, and things like, for example, electromagnetically induced transparency. It's kind of the idea to make the medium transparent at resonance is the kinds of things which I've explored in my PhD thesis. And one like theme which of kind of my early work and how kind of I arrived to the kind of things which I'm talking about is that actually to begin with, when I went to Texas, I actually really wanted to be a theorist. But and actually I started working on theoretical kind of problems, but then kind of in the middle of the PhD, my thesis advisor, Marlon Scully, came and said, oh, we have all of these theory ideas, no one is listening for us. We need to really do an experiment, and this is actually, and then he said, oh, and I have figured it out. So I know that there are now cheap lasers and I have a room with empty optical table and you are in charge, That was my introduction to experimental physics.
How did you feel about that?
Well, I did not feel very good, to be maximally honest, But actually, at the end, I was very glad that I had this experience. And actually, I ended up during my PhD building, an experiment which was not super complicated, but I kind of built it from scratch. And I think this is kind of an experience which I really encourage everyone, whoever wants to go in experimental physics, do, right?
Does it mean that you were mostly self-taught when you set up this first
Well,
experiment?
I had some advice from some remarkable people, some of whom I still collaborate and work together. So it's hard to be self-taught completely, but yes, I had some moments where I was a little bit, did not quite know what to do. So. And so when I arrived here to Harvard, so together with several of friends and colleagues, and you should maybe maybe another piece of background. When I arrived here to Harvard, there was no one basically here interested in doing quantum information at this time, and moreover. Despite of the fact that quantum optics as a field was invented in the kind of next door, actually right here in the next kind of office, by Roy Glauber, whom you can also see. There was really no one like doing. I mean, Roy at the time was already not like super young. He was still around. Was fun to talk to, but he was not super active. So there was no one really doing quantum optics either. So. But
what was he known for?
Roy Glauber. Yeah. Guys, a young generation, So
I don't know.
They probably know.
I remember the correlation function. Because that's what I was doing during my
Glauber
PhD.
states.
The G2s.
Glauber states.
I'm not a physicist, so you have to excuse my.
I see. No. Yeah. So Roy, he really. It's kind of it's interesting. So he invented something which is called he popularized something which is called sometimes Glauber coherence states. And while he has not invented them, it's actually it was first, Schrödinger appeared in the papers of Schrödinger. They appeared, but Roy really understood that, that there is like a boundary between quantum and classical effects, and he found a way to kind of describe it, in kind of in terms of correlation functions, and this was really the birth. Of quantum optics. I mean, the light around us, it's all emitted by atoms, right? But this light can be described by classical, equations, But at some point, you cannot describe light by classical equations. And Roy introduced a way of thinking, to how this can, how this can be done.
And so it seems like at that time, when you just arrived to Harvard, I understand the community was mostly focused on solving fundamental questions. And then there was a change of trend towards how to use atomic physics for solving like practical problems. So is it true? Like that's because now most of the groups are, or at least it's like a lot of people are focusing on, let's say, quantum computing.
Yeah. I mean, first of all, I kind of disagree with what you imply as your division between fundamental and practical.
Well, it's like observing Bose-Einstein condensate or electromagnetic induced transparency, observing that properties.
At that point, Bose-Einstein condensation was also viewed to be as a tool. And for example, one motivation for developing, for this, exploring was a condensation was to make atom interferometers. And atom interferometers are actually useful, practically useful devices. And in the same spirit, I would not say that, quantum computing is just purely practical problem. I think it's actually a fundamental problem, and in fact, I can explain why it is a fundamental problem. So I think this balance between, pure and kind of basic research and fundamental research and applied physics is, to be honest, is what attracts me to this field.